previous 3 lectures we studied the gyroscopic effect. Mostly we analyzed the effect of the gyroscopic on the whirl frequency and the critical speed, and the approach was quasi-static analysis, in which we did not have any equations which were time dependent. Today we will study the gyroscopic effect by dynamic approach, in which we will be obtaining the governing equation of a simple single disc rotor system in dynamic form. So, time dependent terms will be there in that, and we will be considering the general asynchronous motion of the rotor system. So, basically we will be considering the dynamic analysis of a cantilever rotor with a thin disc, and in this particular case we will start with, let us say we have we are considering a disc like this. This particular disc is having, this is the axis about which it is spinning in the positive axis direction, that is z axis. There are two other axes of this particular disc, x and y. This particular disc is having polar moment of inertia about z axis, that is I p. Because of this spinning, the angular momentum of the disc is, let us say, I p omega in the positive z direction. We restricted the rotation of this particular disc about x axis. So, rotation about x axis is constrained to 0, but it is free to tilt about y axis. We are applying a moment in positive x direction, mx, for a small time duration, let us say delta t. And because of this moment which we applied for small duration time delta t, there will be change in the angular momentum. Let us say that is this, because this is the change in the angular momentum, and this particular angular momentum direction would be in the direction of the moment applied, that is this one, this direction, which will be along the x axis. So, to close this vector, we have drawn this particular line. Now, this particular angle is the small tilt of the disc about y axis. So, this is in the positive y direction, this is the tilt of the disc about y axis because of the change in the angular momentum. Now, this particular change in angular momentum, and so from this figure we can able to relate the angular momentum, change in angular momentum due to the moment, and from this vector we can able to see that this particular change is nothing but I p omega, and that small angle which the disc got tilted because of this particular moment. And we can able to write this as this moment, sorry, this is x, which is nothing but gyroscopic moment, is I p omega delta psi by delta t, and for limit when delta t tends to 0, we will be having this gyroscopic moment as ip omega del phi by del t, and this particular angular velocity we are writing as ip omega phi y dot, because is tilting about y axis. So let us write that particular gyroscopic moment again here about y axis. So this is the angular velocity of the disk about y axis. This is called precession. Precession of disk. So we have obtained gyroscopic moment when we gave a moment about x axis to a disk which was spinning about z axis. We need to precess that particular disk about the third axis, that is y axis. So other way, if we want to, in other words, if a particular disk is spinning, if we are giving a precision to that particular disk about, let us say, y axis, then we need to apply a moment in x axis so that we can able to this particular the system is in equilibrium. That means the angular momentum need to be balanced, and because of that we need to apply a moment about x axis. So both ways it is valid. Now let us consider a disk, the same disk. Now we will be applying the moment about the other axis. So let us say this is spinning about z axis. We have x and y axis, horizontal and vertical axis. We are applying, let us say, moment in positive y direction, my. This particular moment is not in positive m direction. This is from top. If we look, it is clockwise. That means this particular moment direction is toward the downward direction about the y axis. Now the original angular momentum is this one, which is along the z axis, and this particular moment which we have applied about y axis, let us say, is for a small duration this. So this my into dy dt is nothing but the change in angular momentum in the direction of the moment applied. So this is the change in the angular momentum, the direction of this particular moment applied, and to have equilibrium we need to close this particular angular momentum vector, and this angle is the precession or tilt of the disk about x axis. So let us say this is delta theta. In this particular case we have restricted the rotation of the disk about y axis, only we are allowing the rotation about the x axis. So from this we can able to relate this particular vector which is in y direction to the change in angular momentum due to this tilt, and this we can able to write it as in this particular case sign is opposite because this particular displacement is in the positive direction, and we have, I am repeating from this. So from this vector diagram we can able to see that direction of the angular momentum, change in angular momentum is in the negative y direction, but the the tilt is in the positive x direction. So, when we balance this particular change in angular momentum, it should be negative, because in negative direction should be equal to I p omega delta theta. This can be written as dy as minus of I p omega delta theta by delta t, and in limit this can be written as minus I p omega delta theta by delta t, and this I am expressing as I p omega delta dot about x axis. So, this is the angular velocity about the x axis. So, this is the gyroscopic moment which will be acting about y axis if we are giving a precision about x axis by delta x. In this particular analysis, we took very special case when we restricted the motion in one of the direction, that is tilting in one of the direction, and we gave tilting, we allowed the motion in other direction. But in actual practice, both the axis x and y, this particular disc will be having precession. So, simultaneously we will be having angular velocity of these two about these two axes, and apart from this we will be having the angular acceleration of this particular disc about two axes, and the moment which we are talking about, which we are applying about the x axis or y axis, actually that moment will be summation of not only due to the precession, but also due to the angular acceleration. So, we need to add these angular acceleration terms also in this particular expression, and we can able to write like the moment about x axis, total moment, which should be equal to I d, this is the angular acceleration term, plus whatever the gyroscopic moment which we obtained earlier. Similarly, in about y axis, this will be I d, this is the due to the angular acceleration. So, basically if you see, this particular equation is similar to the Newton's law, in which we are equating the sum of all the external forces acting on to the disc to the inertia term, because this particular term and both are inertia term. One is coming from the because of the diametral mass moment of inertia of the disc, another due to the polar mass moment of inertia of the disc, and while obtaining the equation of motion, we need to consider these two inertia terms. Now, once we obtain the moment inertia terms, now we can able to take the free body diagram of the disc not only for the rotational motion, but also for the translatory motion, and then we can able to get the equation of motion. So, if I am taking the free body diagram, let us say of the disc in the one of the plane, let us say z x plane, in which y axis is outside the screen, that will be perpendicular to the screen, and it is coming outside the screen. Our disc is somewhere here, is having tilting in according to the positive convention, that is, this is about the y axis, because y axis is perpendicular to the screen and outside the screen. So, according to the right hand screw rule, this particular direction will be positive. Now, we can able to see that we will be having because this particular disc is attached to the shaft and we have drawn the free body diagram of that. So, there will be elastic force and there will be moment also. So, let us say this is about y axis, this will restrict the motion of the tilting, and this is opposite to the y direction displacement. Fy is opposite to the y displacement. So, we can able to write the equilibrium equation of this particular disc in y direction. For force balance, this will be, so I am drawing the free body diagram of the disc in zx plane. So, this is the disc, this is the x displacement of the disc, translatory displacement. Apart from that, it is tilting in positive y direction, that is phi y. Y axis is perpendicular to the screen and it is coming outside the screen. So, this particular point is representing the tip of the arrow of the y axis, and because of this, displacements will be having fx in downward direction opposite to the displacement. Similarly, we will be having this is elastic force which is coming from the shaft. Apart from that, we will be having moment that will be about y axis opposite to the angular displacement, and this particular elastic moment which will be same as that will be actually basically reaction due to all the forces and moments which are acting onto this particular disc. So, now we can able to write the force balance. First, let us say in the x direction. So, this is the summation of all the external force in the x direction should be equal to mass and acceleration of the disc in that direction. Then regarding moment, we have this is let us say y z. I am writing this as zx plane moment, which is this one zx moment. This is the external moment. So, now we are, once we have done the force balance in x direction, the moment balance will be zx, and this is equal to the inertia, which is the second one, id phi double dot y minus ip omega phi x dot. So, this is the equation of motion in x direction, and that is the moment balance in yz plane. On the same line, we can able to obtain equation of motion in zy plane. For this, let us consider the disc having this y displacement and tilting is in the positive x direction, that is phi x. X axis is perpendicular to the screen, but is going into the screen. So, cross is representing that we are looking into the tail of the vector x vector, which is inside the screen. Because of these displacements from shaft, we will be having elastic force, reaction force. Apart from that, we will be having reaction moment from the shaft, that will be y z. Now, we can able to write the force balance. So, external force is this one, should be equal to inertia of the disc in y direction. This is the inertia in y direction. This and then moment balance. This will be equal to the first thing is due to the angular acceleration in this particular plane, that is phi x double dot, and the gyroscopic couple IP omega phi dot y. Now we can able to see that we have got 4 equations of motion. They are x double dot plus fx is equal to 0 and y double dot fy is equal to 0. Similarly, the moment from moment balance we have id phi double dot y minus ip omega phi x plus mzx is equal to 0, previous equation, and then we have the 4th equation. These are the velocity plus myz is equal to 0. Now we need to relate these elastic force with the shaft displacement, that is linear and angular displacement, through the influence coefficients. So these we can able to relate these forces and moments. We can able to relate like this. Here we have influence coefficient, the linear ones, linear angular. I will be defining these influence coefficients. Then angular 0. This is also angular. So earlier we related the x as alpha linear fy plus, that is linear angular zx. So basically all such relations which we had earlier I have put in a matrix form here. Sorry, this is again I am repeating this one. Related the linear displacement x as alpha linear fx plus alpha linear angular m, that is zx, and y as alpha linear fy plus alpha linear angular m yz. Similarly, other two angle, let us say phi y, we have linear angular f, that is fx plus alpha angular m zx, and this last one angular linear fy plus alpha angular yz. So basically these we can able to put in a matrix like displacement, influence coefficient, and the forces. Then this force we can able to get by inverting this influence coefficient matrix into this. So basically this equation is the above one, in which we have the, this is force, this is inverse of the influence coefficient, and this is the displacement vector. This particular equation can be simplified as in terms of, once we take the inverse of this influence coefficient, that will be something like a stiffness term. So, I am writing in those form. So, this will be KLL, L for linear displacement or A for angular displacement. I am writing half of the matrix because this is symmetric. So, now we have related this particular vector through stiffness coefficient and the displacement vector. So, now we can able to go back to this equation of motion. These 4 equation of motion we can able to put in a matrix form, and that particular matrix form, let us say, of those 4 equation of motion would be so here we have substituted for the elastic force and moment also. I will be expanding these matrices for more clarity. Basically, this K matrix is same as the previous one. This is the K matrix, and M matrix is the mass matrix, and based on the ordering of the displacement vector, this will be having this form. This is the diametral mass moment of inertia, these 2 terms. This G is the gyroscopic matrix, which is having most of the terms 0 except 2, which are non-zero. This is IP 0 0 minus IP 0. So, basically this matrix is skew symmetric. This is a gyroscopic matrix. This is mass matrix. This is stiffness matrix. Now, we can able to assume this, because at present we are not considering any external force. We can able to solve for free vibration by assuming the solution of this as, let us say, some amplitude, and the frequency, let us say world frequency is nu, so nu t. So, we can take the derivative of this once. So, we will get this expression, because our equation of motion contain derivative up to second. So, we can derivate up to second, and here these are the amplitude, they are capital X, these are small x. So, these are not time dependent, but these are time dependent. So, if we substitute these equation in the equation of motion, we will get nu square m minus omega nu g plus k, x is common, capital X is equal to 0. So, this has come from the previous equation of motion after substituting the assumed solution. Now, this particular this is a in this particular case, one solution is when x is 0, we can we can able to satisfy this equation. But for non-trivial solution, we need to have the determinant of this equal to 0, and if we take the determinant of this equal to 0 for we will get a polynomial in terms of whirl frequency nu, and the roots of that polynomial will give us the natural frequency of the system. So, in this particular case, we can able to see that this particular determinant is function of nu and omega. We can able to write like this. So, when omega is changing, the spin speed of the rotor is changing, the whirl frequency depends upon that. So, for various value of the whirl frequency spin speed, we need to obtain this particular whirl frequency, and this is nothing but the frequency equation. If we want the critical speed directly, so this particular the frequency equation which we wrote in the previous slide as a functional form, if we substitute various matrices in this, we can able to get a determinant like this. So, we can able to see in this particular equation explicit form of the nu and omega is evident here. So, both nu and omega are appearing. If we take the determinant of this, we will get a polynomial in terms of whirl frequency of the order of 8th degree, and the roots of that will be the whirl frequency, and for each omega spin speed we need to find out. So, we have seen how to get the whirl frequency using obtaining the frequency equation. This particular way of obtaining frequency equation is very crude way of finding. In this particular case, we need to find the roots of that polynomial. In subsequent lecture, we will see that when the equation of motion is having there is velocity terms like x dot in this particular case, it is convenient if we transform these equations in the state space form, and then we can able to convert this second order differential equation to first order differential equation, and in that particular case that will be a standard eigenvalue problem, and that is more easy to solve. So, that particular state space form we will be seeing once we go into the multi degree of freedom system of such rotor bearing system. Again, I am repeating this particular thing. This state space form will again relook into this particular method when we will analyze the rotor bearing system using the finite element method. Now, we will see if we want to calculate the critical speed directly instead of obtaining the whirl frequency with respect to omega. If we are interested in directly obtaining the critical speed, then because critical speed condition is nothing but once the whirl frequency is equal to the spin speed, we can able to get the critical speed directly. So, now let us see how that can be obtained from this equations. So, this is the whirl frequency which is equal to the spin speed, and we are equating that to the forward whirl critical speed, because we have taken the positive sign. That means the whirl direction and the spin direction are same. So, if we substitute this expression in the previous equation, that can be arranged like this, because m was having nu omega square. So, we are having now omega critical f square, g was having nu into omega. Now, they will make a term of omega critical f square. So, that is we have taken common, and this is the K matrix is equal to this. Now, basically in this particular case, you can able to see that this is something like effective mass of the system, and So because of gyroscopic couple, the effective mass is getting decreased, and as we know, the critical speed is nothing but stiffness by effective mass. Effective mass is getting decreased, so we expect that the critical speed will be increasing, and that is, we have already seen that for forward critical speed increases as compared to the backward critical speed. So this is the second case when we have whirl frequency minus of omega, that is backward critical speed, we are defining it. So if we substitute in this equation, we will see that this sign will get changed to positive, and the effective mass will be now m plus g. So here effective mass is increasing. So if we expect that the backward critical speed, this is b, backward critical speed will be decreasing. This particular trend we have seen in the previous quasi-static analysis case also. Now we will take up some example so that whatever the method we have discussed, either the quasi-static or dynamic method, that will be more clear how we can able to get the whirl frequency or critical speed. Especially you will see the Campbell diagram through this example. So one of the example is in which we are considering a long rigid symmetric rotor supported on two identical bearings. The shaft has diameter of 0.2 meter, length of 1 meter. The density of the mass is density of the shaft is given. The support springs are having direct stiffness and is given by this expression. There is no damping we are considering, and we are considering the gyroscopic effect in this particular case, and we are interested in finding the whirl natural frequency at a particular RPM. So this is the rotor system which is supported by springs on two directions. We have been given the values of this particular case, and especially we are interested in this particular case the coupling between the translatory motion and this tilting motion is not there. So we could able to analyze the translatory motion and the tilting motion separately without any problem, and based on our experience, now we can able to write the equation of motion of this system like this. So these two are basically translatory motion, because gyroscopic effect is not present in this. So this will be simpler. So we will not consider this particular thing. So the gyroscopic moment. So you can able to see this is the external moment in YZ plane, and this is the inertia term, one due to the angular acceleration and another is due to the gyroscopic couple. These expressions we in the today's lecture we derived also. So basically we need to obtain what is the effective stiffness, the torsional, this bending stiffness the bearings are providing. If we can obtain that, then our equation of motion can be obtained. So let us see. So because these two equations we can able to get, because if you are giving a x displacement, in x direction two spring will give this much elastic force. Similarly in the y direction this will be the elastic force. The moment from the two bearings will be we can able to get from this, because if you see tilting of the disc about one of the, let us say it is tilting about center of gravity. So if let us say this is phi x, so and total length as we have seen here is L. So we will be having this particular compression or the extension of the spring will be L by 2 L phi x, and because of this K into this much will be the force which will be exerting here, and if we take the moment arm L, we will get the moment due to the springs at the bearing on this particular plane, similarly in other plane. So, basically these are the bending moment which are coming, or the couple which are coming onto the rotor from the bearing, these two. Now, we can able to this particular thing, this particular equation, if you see carefully, these equations are coupled. Unlike the first two equations, they are uncoupled. The first equation contain x only, second contain y only, but here angular displacement phi x and phi y is there. Similarly, here phi y and phi x is there. So, this last two equation we need to solve simultaneously. So, let us, if we assume the solution in this form, we can able to basically write, we can substitute in the previous equation, and we can able to get on the same line as in the previous case this particular homogeneous equation. And if we want the non-trivial solution of this particular determinant, we need to keep it 0. So, if we keep that particular 0, because the first two equations were uncoupled, so we will get the natural frequency from them directly, this one, but the second two equation, the third and fourth equation, will give us the whirl frequency like this, which will depend upon the spin speed also. So, you can able to see that the whirl frequency is now depend upon the spin speed due to the gyroscopic couple. So, if you substitute especially the second and third equation, this one, various values for 10,000 RPM, we can able to get the third and fourth natural frequency like this. Now, now we will take another example in which we will be considering coupling in more general form. So, let us say we have one rotor like this, in which we have offset disc and various parameters are given here: mass, ID, IP of the disc, span of the disc, the particular span of the shaft, Young's modulus, the position of the disc, all the dimensions are given here. Influence coefficient for the simply supported beam with offset discs are defined like this. So, for a given value we can able to obtain them. If we recall from the third lecture, when we considered the general motion of a disc, this was the frequency equation we got it, in which we had the spin, the non-dimensional spin ratio, coupling effect, disc effect. These can be calculated for the given values, and if we substitute this in the equation, this frequency equation, we will get a polynomial like this, which is a frequency equation. For forward whirl, we have condition this one, that the whirl frequency is equal to spin speed ratio. If we substitute this to get the critical speed, the first critical speed, you can able to see the previous polynomial which was containing both this will reduce to a simple quadratic equation in terms of omega square. So, they can be solved, but here one of the root is coming negative. This we have observed earlier also, that one of the forward critical speed is not feasible, only the one is feasible, another is not feasible. So, feasible critical speed we can able to, because we have defined the omega bar like this. So, the forward critical speed, one of them which is feasible, can be obtained from this expression, because this value is this one, this is not feasible. So, from this we will get the first critical speed like this, but second is not feasible. So, we are not obtaining that. But for backward whirl, if we substitute this expression, we will see that the polynomial will reduce to this. in this particular case we will be having two positive roots, and we will be getting correspondingly first backward critical speed and the second backward critical speed, both are in radians per second. Now, let us see if we want to plot the frequency equation as it is without solving the critical speed. So, you can see that this particular expression can be rearranged and we can able to write like this: omega bar is equal to this expression. Now, we can take various value of nu and we can able to get the omega. If we plot this for various value of nu and omega, we will get a diagram like this. This is called Campbell diagram. So, horizontal axis is omega bar and vertical axis is nu bar. So, you can able to see that we have these two lines, the splitting of the natural frequency is taking place, but splitting is less for the first wall. You can able to see this green line is nothing but nu is equal to omega line, that is the critical speed line. So, wherever this particular line is intersecting the frequency curves, there the critical speed. So, upper part is this one, which we have seen the one of the root was we got this for the forward wall, similarly for the backward wall. So, there are two roots here, one for forward and lower one is for backward. For second, this dotted one is the second backward, that was feasible, but this line is not intersecting the second forward wall, and this is evident from here. We will not get the roots because they are not intersecting. So, that is not feasible. So, this particular thing, another thing you can able to see at 0 speed, both the frequency which got splitted because of gyroscopic couple is converging to the same place. So, they are at these two values are at the same place for 0 speed because gyroscopic couple is not there. So, this splitting is due to the gyroscopic couple. Today we saw the derivation of the equation of motion of a simple disk due to the gyroscopic couple, how we could able to get especially the inertia in the rotary inertia, and again I am repeating the last sentence. We have seen that how the gyroscopic couple affects the equation of motion, and especially the moment equations which we obtained were containing this gyroscopic couple, and this gyroscopic couple were coupling these two equations because as we know, when we apply a moment to a spinning disk in one plane, the precession take place in the third axis. So, by that way all the three axes, all the three planes of the rotor system get coupled, especially in the moment equation. And through some example we have seen how to obtain the critical speed or whirl frequency, especially we have seen the Campbell diagram and how we can able to get the critical speeds through the intersection of the line which is 45 degree to the x and y axis.